In this set of notes, we return to the earlier example where we have two interconnected tanks with just water flowing from the outside into the first tank, then to the second, and cascading out from there. We've reduced the coefficients in here based on all the values in the problem, so nothing fancy happened there, just doing some calculations. And what our goal is now is to predict what's actually going to happen to the salt in these two tanks. And how are we going to predict that? We're going to get two functions. The concentration in tank A is a function of time, and the concentration in tank B. So how are we going to accomplish that? Well, what we're going to need to do is find, let's give this a name here, let's call this x of t. We're going to need to find the corresponding homogeneous solution first. And that means finding the eigenvalues and eigenvectors for this matrix A, call that A. And that procedure is straightforward, so we won't go through all the details here. It's just a 2 by 2 matrix. And in fact, with this nice diagonal structure here, we get the nice values. R1 is -1/10, and R2 is -1/20. Just because we have a 0 in the upper right here, we get a nice simple polynomial. The corresponding eigenvectors are 1, -1, and 0 and 1. So with that, we immediately get our corresponding homogeneous solution is C1 e to the negative t over 10. So grabbing this part here times the eigenvector 1, -1, plus another coefficient e to the negative t over 20. So we see some exponential decays in our concentrations over time. That's not a big surprise. We expect things to go to an asymptote, but we still haven't accounted for everything. We've got everything except for the non-homogeneous part. Let's take a look at that next. To find the non-homogeneous part of the solution, what we're going to need to do is assume a form based on the right-hand side, but the differential family, again, I keep saying right-hand side, the non-homogeneous term, the differential family here is just a constant function. So what we're going to get is that constant function times some vector, let's call it u, and that's it. What do we do? We're going to sub that into our differential equation, which is going to get pretty boring pretty quick because the differential equation has a derivative on the left-hand side. So we're going to get d dt of a vector u, and this u is constant, so that's going to be zeros. But that's going to equal, more importantly here, our -1/10, 1/20, -1/20, 0, times our u vector here, plus 3 and 0. So just copying this out, but replacing the vector in both cases with this u vector. As I said, this is going to be a 0 vector, and to make this work out, let's put u1 and u2 as scalars. We're going to have 0 equals -u1 over 10 plus 3, and in the next line we're going to have 0 equals 1/20th u1 minus 1/20th u2. This equation is pretty easy to solve. We bring this over, and we're going to get u1 equals 30. Then we can take that and put it into here, and this just gives us u2 is equal to u1, so it is also going to equal 30. And so our x non-homogeneous is going to be a simple vector of 30 and 30. And if you think of the units, this is Ca and Cb in disguise, concentration in tank A, concentration in tank B, grams per liter. Not too surprisingly, 30 grams per liter is the incoming concentration, and we said in the long run we're going to have 30 grams per liter everywhere, so 30 grams per liter being part of our solution is not as surprising as it might seem. What we can do now is write out our general solution. Ca and Cb are C1 e to the minus t over 10 times its eigenvector, 1, -1, plus C2 e to the negative t over 20 times its eigenvector, 0, 1, plus our new 30, 30 constant value. And what we see is as this goes to 0 and this goes to 0 with time going to infinity, this whole thing is going to approach 30 over 30 which again matches our intuition. Over time, eventually all the water in here to start with is going to get replaced with the salt water at 30 grams per liter. The last remaining point to solve is what happens, or what's the effect of having the initial concentrations in both tanks being 0. What we're going to do is use these two facts to solve for C1 and C2. The first step of that is simply to sub in Ca equals 0, Cb equals 0, and T equals 0. That's going to give us 0 and 0 equals C1. E to the 0 is 1, so it goes away. And we get a C2 times 0, 1 plus our 30, 30. Quickly breaking this down into components, we get 0 equals C1 plus 30, so we get C1 as negative 30. And then the second row here gives us 0 equals minus C1 plus C2 plus 30. Bring that over, bring that over. That gives us C2 as minus 30 plus C1, which is negative 60. And so our final solution is Ca Cb equals minus 30 e to the minus t over 10 times this value minus 1 minus 1 plus C2 we just found was minus 60 e to the minus t over 20 times the 0, 1 vector plus our 30 and 30. From that vector form, we can find what Ca is the first component of everything with the scalars included, and Cb is the second component, again with all the scalars included. That leads to the graphs on the following page. When we rewrite the solutions simply as two elements, Ca and Cb, we see the combination. In fact, this one's easy to match up to the graph here because we have a baseline of 30, and then we have an exponential decay that's upside down, so an exponential decay that's upside down fading towards that 30 line. The other solution is more intricate because it involves the trade-off of two exponentials, and what we get there is that 0 slope to start with, then the S-bend up, and then gradually the approach to the 30 grams per liter concentration coming from the inflow water. What I would say is the most important element of this particular application is just that combination, or that tying in of the ideas of some very simple physics, or chemistry in this case, and the power to be able to mathematize all of the pieces of that puzzle and then predict into the future what's going to happen. And these predictions make complete sense, but they're much more quantitative than we can get from any rough look at the structure of the system itself. So it's a very powerful technique to be able to go from this kind of diagrammatic model to a real prediction of what's going to happen in the future.